All right, yeah, guys, about how the motors are wired. This is a 24-volt motors. These are wired like this. So Dave Hall, this is the way you would want to wire yours. Dave Stapley, yours are in series, so you'd have to go in like from one and then jump up to the other. And then let me see here. It's kind of hard to do backwards. So you'd want to, let's say, positive in here. Yeah. So you'd have to go positive in here, and then you'd have to jump up to the negative here, and then out the positive here, and then back up to here, and then back out. Yeah, I think I did that right. It's hard to do. But yeah, the reason I chose 24 volts is because two 12-volt motors operating off a 24-volt source wired in series are going to need to draw twice the amount of current. Um, because they're 12 volts. So they have to draw twice the amount of current to get the same amount of output torque as a 24 volt version. The other thing is too, if you have a motor that is slightly weaker than the other, um, when they're wired in series, the stronger motor is going to be doing even more work than the weaker one. And also, if you have a motor that's starting to fail, um, you'll lose the whole drive. In this configuration, if one motor fails, unless it's like a dead short, if one motor fails, the other one still will be running. Of course, at half the output torque, but still, yeah, the robot will still move. Um, Oh, let me see here. So that's the way I did, I did this. There's some capacitors on there. You can kind of see how they're wired. I think they're like zero point 0.1 or zero point zero 0.01 microfarad ceramic capacitors. Um, and they're wired in that configuration from what I'd looked online, and yep, they're sourced to the soldered to the can. Just take a file, hit that a little bit, and then you can a high wattage iron. Don't try to use a low one because it'll take you forever. You'll heat up the can. You could damage the any plastic parts like where the brushes are, the plastic holders for them. But yeah, high wattage iron. You know, get some solder on there. Fold the wire over with pre-tinned, and then hit the two of them, and boom, you're done. Um, so that's why I chose this particular configuration. Now, don't, the reason I did it like this is, instead of just like the wires, two wires coming in straight, why did I do it like this? Um, it's quite simple. If it's resistance of the wires, this is just a little bit of wire here, but there's a large amount of current that could potentially flow through here. And that little bit of extra resistance, jumping from one motor to the other, um, could basically let's say this one, the power's coming in, this one's getting 24 volts, it goes across this, maybe it's like a slight volt resistance here. This one, only getting 23.9, so this one's always under volted, which is why it's wired this way. And Andrew, or Martin, is actually the one that told me about that. He is an aircraft mechanic, a friend of his. They built an aircraft, and they couldn't figure out why the runway lights in the aircraft were, the aisleway lights, why they were bright at one end and dim at the other. And they were thinking it was a big huge wiring issue, and it turned out what it was is basically, they had the positive and negative both connected at one end of the aircraft, and then as the wires got longer and the resistances added up, the lights got dimmer as it went down because of the voltage drop. So they simply put a positive at one end of the aircraft, the negative at the other end of the aircraft. The lights were all wired in parallel, and boom, all the lights were equal brightness then. Um, so that's why I wired it in this particular manner. And the capacitors are meant to control the voltage spikes and stuff. Um, so yeah. Oh, the other thing I want to add too, okay, is you're not going to be able, in theory, you're not going to be able to set your controller to the same neutral point on each side. One side will run faster than the other, okay? Uh, Got to sneeze, I think, maybe. Yeah, no. Guess not. Okay, so one side will run faster than the other because all motors, all DC motors are usually biased or timed in a particular direction. They run faster, forward or reverse. If you've done RC cars with the old school DC motors, you know this. They have an actual, you can adjust the end bell to adjust the timing to get a little bit more speed or torque off the line, so on and so forth. So these things are pretty much, they're not neutral timed. So since we're doing a flipped configuration, one set of motors is, if the robot's going forward, one set of motors is running clockwise. The other side, because it's flipped, actually has to run counterclockwise, okay, to have both track drives going forward. So that means that because of that, one set will run slower than the other. So in software or in hard, whatever, you'll need to, tweak that so that when you push your stick forward, both sides are equally running at the same speed, which basically means the faster side will have to be turned down just a hair so that both are in synchronization with each other. Um, so yeah. And I don't know if I covered it. I already recorded this video once and had to stop because I made a mistake. I had a brain fart, couldn't remember. So why did I go with the 12-volt motors as opposed to 24? Because 12-volt motors will draw more current. They require more current. Oh, and the other more current, which means you're going to need heavier wiring, so on and so forth. The other thing too is, why are these wired in parallel? Yeah, because in series, all the current has to flow through one motor to get to the other motor. So it has to flow, it has to flow through the brushes. Yeah, so all that current has to flow through everything. With this, it's divided, if this one needs a little bit more current, is drawing a little bit more current, doesn't hurt the other one. With the series connection, it's like a game of tug of war. If one, yeah, they're constantly kind of trying to find an equilibrium. So again, that's why I did the parallel connection in there. And in this application, yeah, it keeps the motors in synchronization with each other. Both motor can kind of independently draw whatever it needs to draw for current for both motors to find their happy place. So yeah, so that's how I did it. I'll show you here again. It's very simple. Again, positive, negative really don't make a rat's ass worth of difference because we're running them forward and reverse. So it doesn't, it's just for the sake of wiring it, color coding it, making it a little bit easier. And I used, for this short length run here, I used, what was it, 12 gauge wire? Yeah, 12. Yep, 12 gauge. This is high strand count silicone jacketed wire. It's extremely flexible and it has a very high strand count. Don't use solid wire. Yeah, you want to use something nice and flexible. There's a lot, yeah, there's no suspension in the robot, as you know. So it's just one of those things that you want everything to be able to move around and rock and roll a little bit. So hopefully that helped you guys out. If I got anything wrong in there, yeah, just Google it. But the reason I wired it the way I did and it chose the motors I did, so on and so forth. Yeah, there you go. Um, yeah, I'm trying to think if there's anything else. Yeah, I think that's about it. So the caps are in there to control voltage spikes, to keep the line noise back into the controller down. And yeah. Oh, and the other thing is, yeah, with the series connection, don't know if I mentioned it again, but if one motor fails, you lose the entire drive. You lose that track drive. With the parallel configuration, if for whatever reason this one grenades on you, or a brush comes loose or something, you still have one motor to limp the robot back to where you're going. It's going to draw more current, yes, but you want the failure of one's not going to result in, yeah, it's a redundancy, a double redundancy doing it this way. But I can understand, hey, if you got 12-volt motors, you got to wire them in series. You don't have a choice unless you drop that 24 volts down to 12 volts, which is a whole new can of freaking worms. So, all right, that's it, guys. Hope this helped. All right, bye for now.